In this video, we are going to talk about percent yields of chemical reactions. Before that, though, I want to do a quick review. So remember, whenever we're converting between grams of a substance, so I'm going to use A here just to represent a particular substance, and moles of that same substance, so moles of A, we're going to use its molar mass. I'm using A just, again, to make sure that you know that it's the same substance, so grams of water to moles of water. Moles of carbon dioxide to grams of carbon dioxide, moles of calcium carbonate to grams of calcium carbonate. So between grams and moles of the same substance, molar mass is going to be our conversion for that. So molar mass of whatever A is. We did have, I think it was back in chapter 3, that if we wanted to convert between the moles of something and the number of those things, right, the number of particles, so moles of A, and then the actual number of A's, whatever it happens to be. So if I wanted to go between moles of sodium chloride and the number of sodium chloride compounds, or moles of oxygen and the number of molecules of oxygen, whatever it happens to be, this is where we're going to use Avogadro's number. Remember, Avogadro's number is the number of things in a mole of that thing, right? If I had a dozen donuts, I had 12 donuts. If I have a mole of donuts, I have 6.022 times 10 to the 23rd donuts, right? Avogadro's number tells me the number of items, whatever it happens to be, in a mole. So it's per mole for its units. We then added in this chapter that if we wanted to go between the number of moles of one substance, so A, and the number of moles of another substance, B, I'm going to use the coefficients in my balanced equation. So, right, grams to moles, molar mass, but between the same substance again, right? Moles to the number of whatever that happens to be, Avogadro's number, but again, it's the same substance. The only way we've had so far to go between one substance and another substance is to use those coefficients. And again, you could replace moles with the microscopic version, so we could say compounds of A to compounds of B, we would use those coefficients. But regardless, if you're going to go from one substance, A, to a different substance, B, we need to use those coefficients. Remember, it's never going to represent grams. Those coefficients are never going to be grams. So if we're given mass of A and we need to get to mass of B, we're going to have to convert from mass, so grams, to moles using my molar mass. Then from moles of one to moles of the other using those coefficients, and then moles back to grams of my new substance using the molar mass of that new substance. So today, percent yields. So just yields in general. So yields of chemical reactions. So far we've been assuming that all reactions go to completion, right? All of my reactants are converted to products. And well, theoretically this is true. In practice, that's rarely true. So it doesn't always work that way in lab. So we're going to define two terms, theoretical yield and theoretical yield is what we should get. So this is the amount of product calculated to form if all of the reactants are converted to products. So theoretical yield, the amount of product calculated to form if all reactants are converted to product. Right, this is based on the stoichiometry of our reaction. right? This is what we've been calculating, right? Given a balanced chemical equation and you start out with this many grams of a reactant, how many grams of a product are we going to get? That is my theoretical yield. Actual yield, and it's lovely that the name tells us what it is how much we actually will get. So if you go into lab and you perform a reaction, the amount of product that you actually get. Right? Usually reactions involve, in lab, they're going to involve transferring it from one container to another. We don't always get every little molecule out of there, that sort of thing. So the amount of products actually formed. Generally, this number is smaller than the theoretical yield, but if it ends up wet, right, if you have some sort of solvent in there at some point and then you have to dry it, if you don't dry it all the way, then your actual yield can actually be larger because it would include the mass of that solvent. So generally smaller than the theoretical yield, but it doesn't need to be. Oftentimes in lab, our actual yields come out larger because we don't always have the patience to wait for it to dry completely. So usually less. Than theoretical. Theoretical is our predicted, right? Yeah, sorry guys here. So usually less than theoretical, right? Theoretical is our predicted, but not always, right? If it includes the mass of water, then it's actually going to be larger. So our percent yield is going to be how much we actually get. So actual divided by how much we should get, our theoretical yield. And then because it's a percent, we multiply it by 100. An example for us. So our reaction, I'm going to have C4H8 plus CH4O going to C5H12O. And our problem, we want to know what is the percent yield if 32.8 grams of C5H12O is obtained from the reaction of 26.3 grams of C4H8. And we're assuming we have enough methanol. Methanol is the CH4O. So our problem, we do always want to make sure that our reaction is balanced to start, and this one actually is. On my product side, I have 5 carbons, that's a 5. And then on my reactant side, I have 4 plus 1, which is 5. I have 12 hydrogen on my product side. On my reactant side, I have 8 plus 4, which is 12, and then 1 oxygen each. So these do have coefficients of 1. Again, you don't need to write them. If they didn't have coefficients of 1, do double check though. Make sure that they're correct before we start, because we are going to use those coefficients. The next thing in this problem is we're given 2 numbers. So what we want to do is we want to kind of figure out what these are. So this 32.8 grams, not that that looks like an 8, but it is. Let me try to fix it. It's an 8. This here is my actual yield. So this is obtained. So it's the wording, and it's also that it's the product. So what is the percent yield if 32.8 grams of my product is attained? So this is my actual yield. The actual yield would need to be given to us, or we would have the percent yield and then we would go backwards and calculate the actual yield. But I need to have one of those two. Either the percent yield needs to be given or the actual yield needs to be given. Or you're actually in lab doing this and you're determining it yourself. But in lecture, I would have to give you that number. The other number is the one that we're going to use to solve for our theoretical yield. So we're given 26.3 grams of my reactant, of one of my reactants. We're going to convert that to grams of product using stoichiometry. Once we get that number, we can divide it into my actual yield to figure out our percent yield. So we do need some molar masses. So let's figure those out first. C4H8. I'm going to have 4 carbons, so 4 times 12.01, and then it is grams per mole. 8 times 1.01 grams per mole. So I'm grabbing my calculator here. And I get 56.12 grams per mole. And then C5H12O. I have 5 carbons. I have 8 hydrogen. And I have 1 oxygen, 16. Oop, 12 hydrogen. As I was typing into my calculator, I'm like, that's not right. And I got 88.17 grams per mole for its molar mass. So my problem, I'm going to start out with the 26.3 grams C4H8. Because grams are on the top, they're going to need to go on the bottom, so we're going to divide by its molar mass. When I do that, grams are going to cancel. I now have moles of C4H8 on the top. I know the coefficients are 1-to-1, so mathematically we could skip this step, but we're not going to. They're not always going to be 1-to-1. And then also, it's not just moles that are the unit, but the identity of the substance is also. And we do need to convert from one substance to another, so I am going to include these coefficients in my work. When you're getting graded on this, you do get graded in 3 steps. Are you going from grams to moles? Are you going from moles to moles? And are you going from moles to grams? So there are points for this step. Please do not skip it, even when it's 1-to-1. So because I have 1 mole of C4H8 for every 1 mole of C5H12O. The C4H8 one on the bottom because it was on the top and I need them to cancel. I now have moles of my product. We're going to convert to grams using its molar mass. Since moles are on the top, moles go on the bottom, so my molar mass is going to go on the top this time. And then they're going to cancel on us. So again, I'm going to grab my calculator. And I got 41.3 grams of C5H12O. So this is my theoretical yield. So our problem wanted our percent yield, so one last step. I'm going to take my actual, which was up here, 32.8. I'm going to divide it by my theoretical yield, 41.3. I'm going to multiply that by 100. The only units I'm going to have is my percent sign. Those grams are going to cancel each other out. So it doesn't really have units. And I got 79.4%.